My next speaker is Mike Blake. He will tell us about post-skipping and many-body quantum chaos. Please, 45 minutes.
Great. Thanks then for the introduction and for organising this. It's great to have this sort of initiative to be able to talk. Over the last, what I'm going to talk about actually is I'm quite glad to be talking to a holography audience, because what I want to tell you about today is some work we've been doing over the last few years, where mostly our main interest was in understanding this idea of chaos in many-body quantum systems. And so what I focused on for most of the last few years is on some surprising connections between this idea of chaos in many-body systems, starting with holographic systems and then looking at other systems, and seeing it was related to some other questions. Okay, so in particular seeing that it was related to aspects of hydrodynamics and transport and energy dynamics. Okay. So today, I'm not actually going to motivate it too much at the start from that point of view, although have in mind that that's really ultimately where I think the interesting aspect of this is going. But I want to explain to you how this work led to a surprising connection between, well, a surprising new diagnostic of chaos that one can see, which in many ways is simpler than things like out-of-time ordered correlation functions. And that's through a phenomenon which we call pole skipping. Okay, and so moreover, actually, one of the reasons I'm interested in, I'm glad to talk here, I hope to get some people's opinions on this, is we'll see this is related to something extremely simple that goes on when you try and compute correlation functions in holography. And I think it's something that, at least in general, hasn't, at least I didn't know of before, and I think is extremely general and extremely simple. So I think it's something that's of general interest just from a mathematical point of view to anyone who's learned how to study a scalar field in holography. And so I'll explain that in the first part of the talk before explaining this connection to chaos. Okay, good. So as I said, this is just essentially summarizing some of the things I just said there in a bit more detail. So there's been much recent interest, of course, in this idea of diagnosing chaos in many-body systems. And in particular, the kind of normal, well, there are many diagnostics for chaos, but one that people have proposed and studied in a huge amount of detail is this out-of-time ordered correlation functions. So typically we like to characterize chaos by taking our quantum system and we compute these types of correlation function where V and W are just some generic operators, simple operators, and we choose them so that at an initial time t equals 0, they're very simple operators and their commutator will be small. But as V evolves in time in the Heisenberg picture and becomes more and more complicated, then this commutator starts to grow. Okay. And so that's a generic feature of quantum systems, interacting quantum systems, and in particular in large N systems like holographic systems, which we'll be mostly interested in today, are just various types of large N quantum system. This growth is typically exponential, and we have this exponential growth parameterized by an analog of a Lyapunov exponent in classical chaos. And also, one of the things over the years that I've been most interested in is understanding the so-called butterfly velocity, describing how these correlations spread out in space. Okay, so this butterfly velocity is essentially some effective speed governing effective light cone speed, governing how this chaos propagates in your system, and lambda is the rate at which it grows if you stay at a particular point. And famously, lambda, of course, is bounded through this bound on chaos in large N systems, bounded by fundamental constants, and then the temperature, inverse temperature, beta 0 here of your system. Okay. So what I want to explain today is, while much focus in studying chaos is focused on the computation of these types of correlation function in all sorts of different systems, at least for these maximally chaotic large N systems that saturate this bound, there are certainly very other signatures of this chaos behavior. Okay. And in particular, as I'll explain towards the end of this talk, this is related to a proposal we had a few years ago that in these maximally chaotic systems, this type of exponential growth actually originates from some hydrodynamic interaction. Okay, so at the core, the origin of this exponential behavior is essentially of hydrodynamic nature. And a result of that theory, a prediction of that theory, was that there should be a direct signature of this chaos, in particular of these parameters lambda and VB that appear in the out-of-time ordered correlation function. We can actually see them in a much more familiar and simple correlation function, which is just the energy density retarded Green's function. Okay. So in particular, what I'm going to claim is that the form of this out-of-time ordered correlator here is actually related to dispersion relations of collective excitations in the energy density Green's function, i.e. it's just this information about lambda and VB is actually already encoded in the behavior of quasi-normal modes in a holographic system, okay? And so it's really something that you can see a connection to far more familiar just two-point correlation functions and Green's functions and collective excitation responses, things we are in some sense much more familiar and intuitive with than the computation of a four-point function like this. Okay. Good. So that's the motivation. In the first part of the talk, though, for the first roughly half of this talk, I'm going to take a bit of a detour and do a mathematical detour and explain, because I think I want to take the opportunity to explain the holographic description of this idea of this pole skipping phenomenon. And so the reason for doing this is ultimately this claim that there's a relationship between this form of the out-of-time ordered correlation function and the energy density Green's function. We were able to prove that as a general result for an extremely general family of holographic systems with classical gravity and matter. And it's going to rely on some of the mathematics that I'm going to describe in the first half of this lecture, of this seminar. I've been doing a lot of lectures of this seminar, and that's to do with computing, essentially, in which I want to explain how the mathematics of this pole skipping phenomenon is related to sort of a new aspect of just solving computing retarded Green's functions for any correlation function in holography. And it's an aspect I don't, at least myself, have never come across before until the last year, okay? So it's something I want to bring to people's attention. Good. So I claim that this idea of chaos has something to do with a phenomenon called pole skipping in the energy density Green's function. So what is that phenomenon? Well, it's very simple. The name is slightly misleading because we named it perhaps before the phenomenon was fully explored. But the idea is that it refers to the statement that we have some Green's function, so just some, would say a retarded Green's function of some operator, and we look at it in Fourier space. Then if we look at it in the complex Fourier plane, where we allow both omega and k in principle to be complex variables, then there can be special locations in this Green's function, i.e. special values of omega and k, at which we have something quite surprising. We have a line of poles intersect with a line of zeros. Okay. So what does this mean? We have, if we draw our pole curve omega of k in the complex plane, we'll see some line along which there's a line of poles. There could be some other line along which there's a line of zeros, a different line in the complex plane, but they will intersect at a certain point. And what I want to claim is that we can actually identify those points very easily in holography, and they're related to something quite surprising. Okay. So in particular, they're going to be related to the breakdown of essentially some ingoing boundary conditions in holographic calculations. So in particular, this idea that there can be these special locations in a Green's function is something that hadn't really been appreciated until the last year or so in generic Green's functions. And we actually first noticed it in the more complicated case in 2018. It was first noticed towards the end of 2018 in the context of this chaos calculation, but it actually happens in much simpler Green's functions as well, okay? So in particular, the fact that you can have this phenomenon at negative Matsubara frequencies, so frequencies that are in the retarded Green's function, you get this phenomenon of pole skipping at negative Matsubara frequencies, so minus I 2 pi Tm, okay, where n is an integer. then in any Green's function in holography, basically, there'll be certain wave vectors. In some cases, these will be complex, and in some cases, they'll be real, okay, at which you get this phenomenon, okay. And so this is a generic feature of holographic correlation functions. And that's interesting because it means that in itself is that interesting that there are these locations where poles and lines of poles and lines of zeros intersect. But kind of the key point from a holographic point of view is that you can actually very easily work out where these places are, okay? So if you expand your equations of motion about the horizon, as I'll explain, what you see is you can systematically identify these points at which you have pole skipping, okay, at which these lines of zeros and poles intersect. And that's some highly non-trivial information about your quantum system, okay? In particular, once you perform this near-horizon expansion of the equations of motion, you can identify these pole skipping points, and what that tells you then is it gives you a set of points where you know there have to be poles and lines of poles in your Green's function passing through, and there have to be lines of zeros. And so what this means is you can actually extract information, as I'll try to illustrate, about the quasi-normal modes of a certain collective excitations of a certain Green's function, just from information encoded in the near-horizon part of the geometry. And so normally, that's normally to understand the dispersion relation of collective excitations of quasi-normal modes, you need to solve the equations everywhere in the bulk. Here, you can actually obtain constraints and information about the dispersion relations simply from doing a near-horizon expansion of your equations and looking for special points at which you can identify that this pole skipping phenomenon must happen. And so I want to really emphasize how easy this is to do, and in principle, the fact that it gives you this very non-trivial information. Okay. So as I said, in the end, we're ultimately going to want to do this to prove this connection between pole skipping and chaos, but I'm going to illustrate it just doing ADS-CFT 101 and considering just a scalar field and computing the retarded Green's function of a scalar operator in ADS-CFT. Okay. So let's go back to what we learned when we first learned how to do a calculation ADS-CFT, and we're just going to consider some scalar operator dual to some massive scalar, let's call its mass m, and it will be on some asymptotically ADS background, and d is the number of boundary spatial dimensions. And let's just write a typical metric in ingoing coordinates. Okay, so we're going to write our typical metric out in ingoing coordinates. V is our ingoing Eddington-Finkelstein coordinate, R is the radial coordinate, X are the boundary spatial dimensions. And so a typical black hole metric, which we'll consider, would have could be parameterized in this way, where we have some emblackening factor here in the time component, and then we have some more general HRR here describing the spatial component. And we're going to allow here to have some matter fields supporting this geometry, so that F of R and T of R could be really arbitrary matter fields. There could be arbitrary matter fields supporting this geometry. We just insist there's some planar black hole, so there's a horizon at R0 where this F vanishes, and we have some non-trivial Hawking temperature. Okay, so that's all we need. And so what we want to do is to say, suppose we want to compute the retarded Green's function of our scalar in this background. Well, if we call our scalar phi, we just do this in the normal way. We can do some Fourier transform with respect to time, well, it's boundary time, and by doing that with respect to the ingoing coordinate v. So omega is just our frequency of the boundary Green's function, and k is our wave vector. Okay, and then we just have the radial dependence factored into this phi. And so the normal thing you do, right, is you expand this equation near the horizon, and you look to find your ingoing and outgoing solutions. Okay, outgoing solutions. Okay, so these powers look a little bit different to normal because we're in ingoing coordinates, not in the normal RT coordinates. So they're shifted slightly from the normal amount. But if you look at the form of phi of r near the horizon, there's two power law solutions vanishing near the horizon, and the power laws alpha well, there's one solution with alpha 1 equals 0, and typically for generic omega, this is your ingoing solution. It's regular. This is a regular solution in ingoing coordinates, so this is our regular solution. And then we also have the other solution, alpha 2 equals I omega over 2 pi t. So this is the outgoing solution, and this one's not regular in ingoing coordinates, typically. So what do? Well, we pick the solution with alpha 1 equals 0 to give us, and then this solution, the ingoing solution, we can solve the differential equation and we can extract the Green's function from it. Okay. So I'm just telling you things that you probably all know. I'm sure you do, but you'll see why I'm emphasizing these points shortly. So we have our unique solution, well, up to normalization, the ingoing solution. We then just expand it near the boundary, and from the coefficients in the expansion near the ADS boundary, we get our retarded Green's function. Okay, and so this prescription is very nice, and we all know it very well. This Son-Steronex prescription. The retarded Green's function, we impose this ingoing boundary condition. We have a second, mathematically, we have a second order differential equation. We impose one boundary condition, this ingoing boundary condition. It gives us a unique up to normalization solution from which we can extract the Green's function. Okay. So now comes the point. This prescription that imposing ingoing boundary conditions gives you a unique solution to the equations of motion is not always valid. Okay, it doesn't always work. Okay, and this, as far as we're aware, wasn't appreciated until these works in the last year or two. Okay, so in particular, if you choose these negative Matsubara frequencies, then you can see from these power laws, there's the potential for something interesting to happen. Okay, so in particular, if you choose this power law, if you look, this alpha 1 solution looks always regular naively. And this alpha 2 solution, if you choose these frequencies, this becomes a positive integer n. Okay, and so this other solution alpha 2 with alpha 2 also looks regular near the horizon. Okay, if you choose yourself to be at these special negative Matsubara frequencies. And so at these frequencies, there's a potential ambiguity. It's not clear just from this simple leading form of the analysis whether these solutions really are irregular or whether irregularities kick in at some higher order in the expansion. Reasonably well known is that typically at typical values of k, what you normally find is that in one of these solutions, you get logarithm terms developing that actually ruin the regularity, and there is indeed normally for these frequencies in generic k, you normally expect there to be logarithm terms that again destroy regularity for one solution and give you a unique solution, okay, after imposing regularity. So this was, at least until we did this work, what we understood to be the case, but it turns out that's again not always true. If you choose, it turns out that there can be, and there generically are, typically n values when you're at these frequencies of wave vector, order n values, at which the logarithms essentially vanish, and both independent solutions are fully consistent with ingoing boundary conditions. Okay, so both solutions to the differential equation at these frequencies and wave vectors are consistent with ingoing and can be written as just regular solutions in ingoing coordinates. And the punchline is what that means is that at these frequencies and wave vectors, there isn't a unique solution, okay? And so the Green's function here can't actually even be uniquely defined at these special frequencies and wave vectors, simply because of this breakdown of this boundary condition, and that leads to pole skipping. Okay. So let me give you some mathematical equations to convince yourself that this actually really does happen, and then you can go away and check this yourself if you really don't believe me that this really is the case. Okay. So what we did to prove this is or what you can do to prove this or to construct this is you're just going to very explicitly look to find solutions to the scalar equation of motion. So you take the equation of motion for your scalar field in ingoing coordinates, and just try and construct series solutions as if you were some undergraduate student trying to solve, series solutions problems in ODEs. Okay, so you take a regular Taylor series solution near the horizon. So it has this form, it's the first two terms. So the first term is specified by some parameter phi0, then we're allowing for another parameter phi1, etc., etc. And of course, typically what you do is you insert this into the equations of motion, and from expanding the equations of motion in powers of r minus r0, what you're going to get is some recursion relations that relate these various parameters to each other, and then you can solve them in order to construct your solutions. And so for this case of omega 1 equals, so normally the typical case that happens is you end up with a single solution parameterized by phi 0, and then the equations of motion determine phi 1 in terms of phi 0, and then at higher order phi 2 in terms of phi 1, etc., giving a unique solution proportional to the amplitude phi 0. But for these negative Matsubara frequencies, essentially that prescription breaks down. So you can see this immediately for this first negative Matsubara frequency, just by taking this parameterization, plugging it into the equation of motion, and looking at what happens at the horizon. So just evaluate the equation of motion for a scalar field at the horizon. And the resulting equation takes this form. And as I said, the key point here is this does what I said it should do. It's some relationship, it's some equation that provides a constraint relating phi 1 to phi 0. Okay, and so for generic values of k and omega, you can solve this for phi 1 in terms of phi 0, and then keep repeating that order by order to get a unique solution parameterized by this variable phi 0. So that's great, but you can see something interesting can happen if I go to this frequency here, omega 1. So the fact that this frequency is the one at which something interesting happens can be seen because if I go to this point, I make this coefficient here of the phi 1 term vanish in this equation. Okay, so if I pick the frequency as such, I can make the coefficient of phi 1 vanish. And then what I could also do is, once I've picked omega to fix this term, if I allow k to be some general variable and to be complex, then I'm guaranteed there's some value of k at which I can make this term proportional to phi 0 vanish as well. So if I move to these special, so that's what's said here. So the special thing that happens is if I move to this frequency, what omega is omega 1 minus 2 pi ti, and then I'm picking k1 squared here to be a special value of k, special value of momentum to make this phi 0 term vanish, then this equation is completely trivial and imposes no constraint on the solution. Okay, so if I choose this to vanish and this to vanish by choosing omega and k, there's no relationship anymore between phi 0 and phi 1. Any phi 0 and phi 1 satisfy this equation. And so I find that I get solutions with two free parameters, okay, phi 0 and phi 1. And so you could worry that maybe at higher order that some constraints between these parameters emerge, but we've done that systematically and that doesn't happen, okay? So what it turns out is that we're able to explicitly construct a two-parameter family of series solutions like this near the horizon, and hence that's only consistent if both independent solutions to the scalar equation of motion are consistent with ingoing boundary conditions. And so I should say that we have lots of actually explicit examples of cases where, say, for instance, you look at a simple case where the actual solutions are known for the scalar field phi, you can indeed check explicitly that you get completely unique, that both solutions to this differential equation for phi, in the cases you can solve it analytically, you can explicitly see you get two independent solutions, okay, that are both regular near the horizon. There's nothing funny going on here with the Taylor series expansion. This really is a general feature of just how scalar fields behave at these frequencies if you choose complex, or in this case, complex momenta, but in some cases, it can be a real momentum as well. Okay. And so that's what I really wanted to really emphasize. There's these special points where the ingoing solution is not uniquely defined in holography, okay? And as I emphasized, this has only recently been appreciated. And the existence of these multiple ingoing solutions is precisely what results in this pole skipping phenomenon in this retarded Green's function. okay? And so the reason for this is that if both independent solutions to the scalar wave equation are ingoing, then any solution is ingoing. There's only two independent solutions, and that means that any solution to the scalar equation of motion is ingoing. So in particular, if I ask about the solution that's normalizable in the UV, okay, so I could ask about the solution for the scalar equation for which phi a vanishes, that's the normalizable solution, and that has a pole in the Green's function, gives a pole in the Green's function. Well, that will definitely be ingoing, okay, because all solutions are ingoing. And likewise, the solution with phi b equals 0 would be ingoing, okay. So there's this ambiguity. The Green's function is not defined because everything is consistent with ingoing boundary conditions. And the result of that is I can always actually find an ingoing solution corresponding to poles or zeros. So actually that's a little bit of a fast explanation. You can make this very rigorous if you actually move to make this rigorous and to rigorously justify that you get poles and zeros passing through this Green's function. You actually need to make the Green's function defined in the first place. And the way you can make it well defined is to move slightly away from this special value of omega and k. And then what you see is that the Green's function, basically, you get a unique, precisely at this point, the Green's function is ill-defined. And in the neighborhood of this point, you get a different answer depending on how you approach this point. Okay, so depending on how you approach this point in the complex frequency momentum plane, you see different values, and if you approach in some directions, you see poles, and if you approach along others, you see zeros. So there's a similar analysis for these higher Matsubara frequencies that I won't describe. It's a bit more complicated, but again, there are special points at which both solutions you can construct more than one ingoing solution. And so mathematically, that's the key fact. But physically, the key implication is that just by writing down this near horizon equation, which I can write down in a second, it's just I take the scalar equation of motion and I write it on the horizon. I can read off that at this frequency and at this wave vector in the boundary Green's function, I can tell you there's definitely a pole passing through that point in the Green's function. And there's definitely a zero passing through that location in the Green's function as well. And so just from a very simple systematic near horizon analysis, you gain this non-trivial information about where the trajectories of your quasi-normal modes are. Good. So before discussing chaos, let me illustrate this using an example. So this is a very simple example. This is the retarded Green's function for a massive scalar field in a BTZ background. Okay, so a three-dimensional black hole, take a massive scalar field and compute its boundary Green's function. So what this left-hand plot shows is the locations of these pole skipping points if you do this near horizon analysis. Okay, so these first 2 points here at omega is -1, that's omega is imaginary part of omega is minus I2, that's omega is minus I2 by t. That's this frequency, and then the values of K1 satisfying that equation for the BTZ black hole. So in that case, you get two pole skipping points at certain values of imaginary K. The K turns out to be imaginary in this case. It's not always imaginary, but it is in this case. So there we go, we get these two pole skipping points. And then if you do the higher N analysis, which I should really say Richard Davison absolutely was the one who understood and pushed through how to understand this higher N analysis. It was really incredibly impressive what he did. And what you find is that then there's two on each side, okay? And then 3 on each side at -3, 4 on each side at -4. There's typically N pole skipping locations. And my claim is that from this near horizon analysis we've done, I'm convinced that I can tell you that there must be lines of zeros and poles intersecting at these points in the Green's function. And so to check that, you can take, in this case, okay, in general, it's not known analytically what the lines of poles are going to be in a Green's function. In this case, it's known what the dispersion relations are because it's this special case. So let's just plot them, okay? So these blue lines are all the lines of zeros in this Green's function. These dotted lines are all these lines of poles in this Green's function. And you'll see they precisely intersect at these points that I've read off from my near horizon analysis. Okay, so just to emphasize, to get these points, all I do is this expansion of the equations of motion and just look at an equation like this or the next highest order equation. And I can read off and tell you what these points are. Okay, so whereas to get these dispersion relations, you need to know the full structure of quasi-normal modes in your system, which you're just not going to know in general in a holographic system. But for any holographic geometry, no matter how complicated it is, you can work out these points and you can use them to constrain the dispersion relations of your poles, okay? And so these points contain really highly non-trivial information about the dispersion relations of your holographic systems. And so I want to explain now how we use that to prove this connection between pole skipping and chaos for the energy density Green's function. Okay, good. So as I said, that was a bit of mathematical background, but I really do think that's quite surprising. And if anyone has seen that before or encountered that before, do let us know, because we haven't been aware of it being discussed in the literature. Okay. So as I said, the motivation and actually the context in which this phenomenon of a breakdown of a near horizon boundary condition was first discovered was in the context of us trying to understand connections between chaos and energy dynamics. So this is something of a pet passion of mine that I've been studying for many years with people like Hong and Richard Davison and Aristos Donos and Sabir in the past, in particular because I'm really convinced there's a very fundamental connection between this idea of chaos in out-of-time ordered correlation functions and energy dynamics. So the first hints of this were these connections we found between diffusion constants in holographic systems and the butterfly velocity. And these were so simple and surprising, it seemed remarkable. And they were also seen in non-holographic systems as well. Okay. And then more conceptually, if you ask yourself what's responsible for the form of the out-of-time ordered correlator in holography, it's a gravitational interaction. And we know gravitational interactions correspond in the boundary theory to stress tensor interactions. And similarly, the SYK model, the one case we have a very simple effective, well, the simplest case, we have more now where we have an effective theory. The Schwarzian theory is responsible for giving you this, this exponential behavior in the OTOC. And that Schwarzian theory is nothing but a theory of the energy dynamics of your system. It's literally a hydrodynamic theory, or it's essentially a hydrodynamic theory. So sort of motivated by these connections, Hong and I and Hyun-Suk in 2018 proposed that actually the fact that in SYK, for instance, it's these hydrodynamic variables that result in chaos, we essentially propose that that should generally be true, at least for maximally chaotic systems. So we constructed an effective field theory description of this exponential growth, where we essentially showed that within this framework that Hong's been developing, this really beautiful framework of hydrodynamic effective field theory, you can actually consistently build a theory that can account for the exponential behavior of OTOCs as coming from an interaction through the stress tensor, governed by hydrodynamic degrees of freedom. Okay. So in particular, the key role was there was essentially a key field in this quantum theory called sigma of t, which is like the time reparameterization field in the Schwarzian. And the thing to bear in mind is that in some sense, this plays the role of a local temperature in normal hydrodynamics. Okay. And you can use this field to build a theory where there's exponential growth in OTOCs, but everything is perfectly consistent and there are no instabilities. And so this theory was really our proposal to try and explain why there were all these connections between hydrodynamics and chaos that seemed to be hinted at. So the reason I'm talking about that today is that this theory predicted a very precise signature of chaos in the energy density Green's function, which at the time we didn't really understand where it was, intuitively, or why it predicted this. It just does. Actually, we have some intuition, but it's really a seemingly odd. If I hadn't motivated this through pole skipping, you'd never have thought to think of it, okay, in the first place. In particular, because this same degree of freedom, sigma of t, is responsible for OTOCs and the energy dynamics, it's the hydrodynamic degree of freedom, that means that there should be some signature of this profile of the OTOC, of this exponential form, just in the energy density Green's function itself, a much simpler observable. Okay. Essentially, this is a 4-point function, and it's related by some interaction in which this field sigma is exchanged, and therefore you'd expect the 2-point function of signature, sigma, or the 2-point function of the energy density Green's function to know about this functional form. So the claim, let me actually go back here, is that the retarded Green's function of the energy density actually exhibits pole skipping, and the frequency at which it exhibits pole skipping are not just some arbitrary point, like for the scalar field. So for the scalar field, it was just some point we could easily figure out using some near horizon expansion. Here, it's at a specific point that's determined, that's related precisely to this form of this correlation function, the OTOC. In particular, if you think of this in Fourier space, the exponential growth in time defines a frequency here, I times lambda. So this now lies in the upper half plane rather than the lower half plane like before. And then this VB defines a wave vector. This spatial dependence exponentially decaying defines a spatial wave vector I lambda over VB. And the claim is that at that value of frequency and that value of momentum related to this exponential form of the OTOC, there is going to be pole skipping in the energy density Green's function. And in particular, that means that a pole in your correlation function, in your energy density correlation function, has to pass through that point, parameterized by these chaos exponents, which, just to emphasize, without this hydrodynamic theory, you'd have no reason to think that this correlation function for the OTOC and these parameters should have anything to do with the retarded Green's function. I'm telling you that there's an incredibly precise signature in the retarded Green's function, precisely at these values, related to these values lambda and VB, at least for maximally chaotic systems. Okay. Is the idea. So let me explain that a bit more, a bit intuitively. So as I said, this effective theory as a consistency condition actually predicts that the retarded Green's function should have both a line of poles passing through this point, okay? So this is pole skipping from our maximally chaotic systems at frequencies I2 pi t. So note, this is very different to what we saw for the scalar field. This has to happen in the upper half plane and at this wave vector, and at some incredibly precise wave vector, I2 pi t over the butterfly velocity, that's related to the form of this OTOC. And as I said, in the kind of other key thing to take away from this is that this means that this point, there has to be a pole in this energy density Green's function passing through it, related to this, and related to the form of the OTOC. And of course, many of us, in particular me, the reason I was so interested in the first place and got interested in energy dynamics and the connection to chaos was that we're often very interested in the behavior of poles in this energy density Green's function, okay? For instance, they have hydrodynamic poles, which begin as being, say, a diffusive pole in typically systems, and then have some higher order corrections at K. So what it turns out to be true is that in all the cases in which we can study this pole skipping, then the pole that passes through this special point is always this line of hydrodynamic poles. And so the statement is that in general, right, we know this leading term in hydrodynamics, but we have no real control over these higher order corrections and what happens to this dispersion relation. But my statement is that I know that because this pole is going to be the one that skips, this pole, whatever these ... dots are, they have to resum so that if I insert this value of K into the dispersion relation, I get this value of frequency. And so it means that this chaos point actually knows about the dispersion relation of this quasi-normal mode and actually could be used to constrain these higher order terms in this dispersion relation for this collector excitation. And this is true not just in holography. We have examples where this happens in CFTs that I'll mention briefly. Okay. So one thing I should emphasize is that actually the fact that this happens for the energy density Green's function was first noticed numerically by these authors here, by Sasha, Conrad, and Vincenzo, in a very nice paper in which they computed the dispersion relation of the hydrodynamic mode just for the holographic system dual to just the ADS5 Schwarzschild black hole, so that the simplest possible ADS system. And what they did is they, without really any reason to look for it, it was really very impressive that they thought to look for something like this. And what they saw was that if you take that dispersion relation, they just observed it passed through this point related to chaos. Okay, they were trying to look for some connection between this dispersion relation and chaos, and they identified that this happened, and they identified that a line of zeros also passed through this point as well. Okay, and so they did this for ADS5/Schwarzschild, and we had a theory, a quantum field theory description that predicted this should happen in general. And so we set out to prove that this happens for a very general class of holographic systems, and we were able to prove it. Okay, so to prove that for basically any theory dual to classical gravity coupled to matter, this will happen, and that there will be a quasi-normal, there will be this pole skipping phenomenon, and a pole passing through this location that's related to the OTOC that you compute in holography. Okay. And moreover, it's been seen actually in these other examples that this also happens in other maximally chaotic systems that are not holographic systems. So for instance, the SYK chain this happens in when it's maximally chaotic, it happens in 1+1D CFTs, and it also happens, I think, in CFT and Rindler space. There was a paper, I think, by Felix and Moshe, and I've forgotten the name of the third author, I think maybe Reeves, I'm not sure, and they computed, they saw it happened in Rindler CFT as well. Okay, so there's now quite a large amount of evidence that this phenomenon does happen always in maximally chaotic systems, and that's some evidence, a lot of evidence, well, some evidence perhaps in support of our effective theory. It's certainly highly non-trivial that it happens. Good. So the reason then I spent so much time explaining that proof beforehand about what happens to pole skipping in a scalar field is that it's this argument that allowed us to prove that this pole skipping happens always in essentially any holographic system, in the very general class of holographic system. Okay. So of course, I want to emphasize again that proving something about all holographic systems and the behavior of quasi-normal modes in all holographic systems is not something you reasonably would expect to be able to do. The only reason we can do that is because ultimately it's this breakdown in a boundary condition that we're looking for. We're not looking to solve the differential equation, we're just looking to identify the points at which the near horizon boundary condition breaks down, and there are multiple ingoing solutions. So that's something you might be able to hope to do in general. You don't have to solve the actual equations. So what we did was we just expanded the linearized Einstein equations near the horizon. And what you find is very much like in the scalar field case, you find one of the equations becomes a trivial equation at the horizon. So of course, this computation is a little bit more complicated because there are many fields. But near the horizon, you find one of the equations which imposes a constraint relating the various near horizon components of the metric to each other. If you choose to be at precisely this value of frequency and this value of wave vector, which are related to the parameter, the holographic form of the shock wave that gives you the OTOC. So you fix these, you go to these locations determined by the holographic shock wave calculation. You just observe empirically that one component of the Einstein equations becomes trivial in exactly the same way that we saw before, and actually imposes no relationship between the near horizon, the parameters in the near horizon expansion. And so the upshot is that at this particular frequency and wave vector, there is again an extra free parameter in the ingoing solution that implies the existence of multiple ingoing solutions, okay, and implies pole skipping. And so we presented in this paper this proof, and then we verified it in very explicit glory detail in several models and computed it numerically, and did it in terms of gauge invariant observables as well. So this definitely happens. And we checked it very explicitly by comparing to dispersion relations of quasi-normal modes and verifying that in all the cases we could, they indeed pass through the predicted point. So finally, another comment to just make is that Sasha then generalized this to the case where you have high derivative corrections in gravity. Again, from the same argument we developed in this paper, is a very simple argument to actually check. It's only a few lines. What you see that in higher derivative gravity, it works as well. So the final slide then that I'll present with some results in is to just illustrate you this idea that this really can give you some information about the hydrodynamic dispersion relations. So numerically, as well as proving this result in general, we took some particular models and we numerically computed the dispersion relations of poles to check that indeed our proof was correct and there was a pole passing through this point. So here is a plot from this axion model that people like to study sometimes. It doesn't really matter if you don't know this model, it's just a holographic system with some matter fields. And what we have here is a plot of this hydrodynamic dispersion relation. So we've taken this dispersion relation of the hydrodynamic pole, and with that k be imaginary, and we're going to just plot this by numerically determining what this dispersion relation is, and plot this as a function of the function of k, where k would be imaginary. Okay. So at small k, it's going to be quadratic, and then it's going to deviate away from quadratic, and I'm telling you it's got to pass through this point, whatever these dots are. And so that's what you see here. So this blue line here is an approximation just by taking the value of that quadratic dispersion relation. So it's valid, this is just assuming the purely quadratic form. And then as I increase k, the dots here are the exact numerical results for the dispersion relation of the quasi-normal mode. You see it starts to deviate from the quadratic form. But what I'm telling you is that that deviation we know has to be such that it passes through this point we've marked through grids, where this point is determined by this wave vector and momentum, this frequency and wave vector are determined by an independent calculation by just whatever the OTOC parameters are, the Lyapunov exponent and the butterfly velocity. So we a priori know what these are, well, not a priori, we know from computing the OTOC what these are, and then that's much easier than computing this dispersion relation of these quasi-normal modes. But I'm telling you, we therefore know that whatever the corrections to the hydrodynamic form are, they have to be such that this dispersion relation passes through this point. And indeed, you see numerically, that's exactly what happens here. And so likewise, this is another example. The quadratic form, we get some deviations in the black dots as we go to large k. In this case, the deviations are less, actually, because we're at much lower temperature. It turns out hydrodynamics, the leading term, does a good job at low temperature. And again, beautifully, these corrections are such that we pass through the special point I'm telling you is related to chaos. And so this is the dispersion relation of the pole. You can also check there are zeros while they're passing through this point by computing essentially the residue of this pole and seeing that the residue vanishes exactly here. Good. So let me end with that. I just wanted to explain this new phenomenon of pole skipping, and in particular how it's related to this breakdown of the near horizon boundary condition in holography. It happened for a scalar field, but for the most interesting case is what that happens for the energy density Green's function, because here the pole skipping point, just to emphasize, is actually related to an independent calculation in your quantum system, which is the calculation of the OTOC. So two completely independent quantities in principle, the OTOC and the energy density Green's function, know about each other in an incredibly precise way. And in general, that would be incredibly hard to believe, and therefore we think it's quite non-trivial evidence in favor of this hydrodynamic theory of maximal chaos, which actually predicts this as a self-consistency condition of this effective theory. And the reason it predicted that is we were attributing the form of the OTOC to coming from an interaction through some hydrodynamic fields. And so that's why there's a connection to the energy density Green's function. So the key open question then is to understand what happens away from maximal chaos. At least in the form I've described so far, this pole skipping seems to be related to maximal chaos. The behavior in the OTOC is much more complicated away from maximal chaos. Many modes contribute essentially to the OTOC, And so it's more complicated, not just the energy density sector. But you could ask, is there some way in which these predictions are modified? And I believe Mark Mazzai has been thinking about that lately and has some interesting thoughts about that. So I don't think necessarily they're written yet, but you know, maybe this is something on which we'll make some progress. People will make some progress soon. It's certainly an interesting question. So thanks. I'll stop there.
Okay. Thank you very much for your very interesting talk. Still, we have some time for questions, please.
I have a short question. Can you hear me?
Yes, sorry.
Yeah, so for scalar perturbations, can you connect for, as I understand, for stress energy tensor, I mean for gravitational perturbation, you can connect the results with butterfly velocity and with Lyapunov exponent. But for example, for scalar perturbations, this is not so, right?
That's right. So for the scalar perturbation in general, it turns out in some cases the point just happens to be the same as the wave vector. In some cases, they might happen to turn out to be the same wave vector, but in general, they're just completely unrelated for the scalar field. So so for the scalar field, this pole skipping point is not connected to chaos at all in any obvious way. I'd say it's just not, personally. But what it is still a way in which, by expanding the scalar wave equation near the horizon, just for other purposes, you would gain some information about the quasi-normal modes in that system. But there wouldn't be a connection between that and chaos, essentially because the scalar equation of motion is nothing to do with the gravitational shock wave calculation in holography, which comes from solving the Einstein equations. Whereas, you know, in order to get, it actually turns out that the near horizon equation that breaks down in the chaos case is precisely the same equation that governs the shock wave for holography. So it's really only the energy density Green's function in holography at which this pole skipping has something to do with chaos. Yeah.
Okay, and what happens for a spinning black hole, for example, if you consider spinning BTZ black hole? Will gravitational perturbation show something special? Because sometimes spinning black holes show very curious results.
It's a good question. It's actually something we're currently working on. So we've been thinking about that lately. I can maybe talk about that some other time. Maybe it's better.
Okay.
Because it's still work in progress with other people, so I probably don't want to tell you what the answer is to all of that right now. But yeah, it's a good question. It's a good question.
And typically, all this is related with near horizon geometry. I mean, it's universal because of near horizon geometry is universal, right? Or this can be connected with ultraviolet properties also?
No, it's because the reason it works is because both the shock wave calculation and the near horizon expansion are, as you say, just near horizon properties and universal. So the only information I need about a geometry in order to identify the pole skipping location for chaos or for any of these places is I only need the IR horizon information. So you don't need any information about the UV form of your metric, say, for instance, to connect it. So you can just, that's the point. You only need to know the horizon, what's going on near the horizon. That's why it's possible.
Okay, thank you.
More questions, please? Okay. If not, let's thank the speaker again. Thank you very much.